Hello everybody and welcome back to Synapse. This is Ritika. This is going to be the first video in the series of 3 videos on action potentials. In this video we shall talk about neuronal action potentials, and in the next 2 videos we shall talk about cardiac action potentials. Let's first know about a few basic terms. Membrane potential is a difference in electric potential between the interior and exterior of a cell. Electrochemical gradient is a combination of electrical and chemical gradient of the ion. Equilibrium potential is the membrane potential at which there is no net flow of an ion. That is, it is the membrane potential at which the electrical gradient is equal and opposite to the chemical gradient of the ion. These are the equilibrium potentials of a few well-known ions. Next we have the conductance. Conductance is the flow of an ion across the cell membrane. Greater the permeability of the membrane towards that ion, greater is the conductance of the membrane towards that ion. What's important for us to understand here is that an ion always diffuses in the direction that brings the membrane potential to its equilibrium potential. That is to say, if the sodium conductance of the membrane increases, then the membrane potential moves towards 70 millivolts. And if the permeability or the conductance increases for potassium, then the membrane potentials are going to move towards minus 95 millivolts. Driving force is membrane potential minus the equilibrium potential. That is, further the membrane potential from the equilibrium potential of an ion, greater is the force driving its movement across the cell membrane. Talking about the channels needed for the production of action potential, first we have the voltage-gated fast sodium channels, which can be observed in 3 configurations, that is closed, open and inactivated, and it has 2 gates, the M gate and the H gate. In the closed configuration, there is very low sodium conductance. In the open configuration, there is very high sodium conductance. And this channel always goes from the closed state to the open state when stimulated, and then to the inactivated state, and only after that back to the closed state. This channel can be stimulated only when it is in the closed state. That is, when the channel is in the open or the inactivated state, it cannot be stimulated. Next, we have the voltage-gated potassium channels, which opens on depolarization, but this is very slow. Thus, the sodium current superimposes the potassium current and causes the depolarization. And once the sodium channels get inactivated, the potassium current through this channel causes repolarization. Now let's look at this action potential. Here, the depolarization starts. Only if this reaches the threshold potential, a critical number of sodium channels open, which is sufficient to cause a further depolarization and the action potential. This increase in the conductance for sodium ions drives the membrane potential close to the equilibrium potential of the sodium, which is plus 70 millivolts. This causes the upstroke of the action potential. But these open sodium channels become inactivated as the membrane potential becomes positive. The potassium current, which had started during the depolarization itself, continues now, taking the membrane potential close to the equilibrium potential of the potassium, that is minus 95 millivolts, causing the repolarization. But by the time it becomes negative enough, these potassium channels close. And here we can see slight hyperpolarization because of the slow closing of the potassium channels. Action potential follows the all or none rule. The action potential occurs only if the threshold is reached. Action potentials cannot summate. An action potential is conducted along an axon without any decrease in the magnitude. The last thing we shall be talking about in this video is about the refractory period. We have two types of refractory period, absolute and relative refractory period. Absolute refractory period is the period during which, no matter how strong the stimulus is, it cannot induce a second action potential. In this phase, most of the sodium channels are either open or in inactivated state. The relative refractory period is a period during which a greater than threshold stimulus is required to induce a second action potential. Here I end this video. I hope it was helpful. Do subscribe if you haven't yet subscribed. Do click on the bell icon. Share the video so that others benefit too. The next two videos are going to be on cardiac action potentials. See you soon. Bye-bye.